Welcome to Calc 3. This is section 14.4. Well, we'll talk about Green's theorem in two different forms. So let's let F be a vector field, C be a smooth curve. Let's let R parameterize C, and T is the unit tangent vector to R. We'll let N be the normal vector that always points to the outside of the curve, and we'll let the direction of the curve be counterclockwise. So with these conditions, we let the flow along the curve be defined by the integral along C of the vector field F dot with the tangent vector T ds, where S is the arc length parameter, equal to the the integral of F, the vector field F dot dr. And the flux across C is equal to the vector field F dot n ds, which if F is equal to m comma n and R is equal to Fg, we can, in two dimensions, shorthand that as the integral over C of m g prime minus n f prime dt. So let's do an example here. So given F is equal to x plus y, comma x minus y, and C is the line from 3, comma negative 2 to 3, comma 2, let's find the flux across C. So we can easily parameterize this with just time going from negative 2 to 2 as our x value, but we can also choose to parameterize it in any particular fashion we want. So let's parameterize this as r equals x is always 3, and let's let y be 2 plus 4t, where here t is an element of 0 to 1. Again, parameterizations are not unique. We could have said r is the parameterization 3 comma t, where t is an element of negative 2 to 2. These parameterizations, again, aren't unique, and so you're allowed to choose whichever parameterization works best for your system. So here in this blue case, r prime is equal to 0, comma 4. Our flux along C is equal in the form m g prime minus n f prime is equal to our m component is x plus y. Our g prime component is 4, minus our n component is x minus y, times our g prime is f prime is 0, dt. Substituting in our x and our y, our times 0 to 1, so we get 3 plus negative 2 plus 4t times 4 dt. So this gives us the integral 0 to 1 of 4 plus 16t dt. This is an easy integral to solve, and we get 12 units of flux across our curve C. So Green's theorem in two dimensions is helpful to find area. So we have two different forms. We have the circulation form or the tangential form. So we have over a closed curve, and this is important, is we have a closed curve C, f dot dr is equal to the double integral of the region of the curl of f dotted with k, where k is our unit vector in the third dimension of dA. So if our curl is equal to 1, then we're essentially finding the area of that region, and we'll see that in a moment. And the flux form is over the closed curve C, f dot n is equal to the divergence of f over that region, so the sum of all the little divergences of f. So let's find the flux across the closed curve C, where C is the boundary of the disk of radius 2 oriented counterclockwise on the surface F, where F is equal to, along the field F, where F is equal to 4x cubed plus sine of y squared, comma 4y cubed plus cosine of x squared. So our goal is to describe a circle, but putting our vector field F into polar coordinates is difficult. So even though we have a circle as our boundary, it may not be the easiest to put it in polar coordinates just yet. So if we were to try to evaluate our vector field and our flux as defined earlier in this f dot n ds, as equal to the vector field C m g prime minus n f prime dt. We can parameterize our curve C would be r is equal to 2 cosine of t, 2 sine of t. But again, putting f into polar coordinates is difficult, so this makes this hard. So if we use Green's theorem, this might make it an easier problem. This is a closed curve because we're dealing with a circle, and our curve is oriented counterclockwise, so we've met the conditions for Green's theorem. So we have a closed curve, C, f dot n dn, or ds, we're looking for flux. So over this region, we're looking for flux, so we're looking at the divergence of f dA. So the divergence of f here is equal to the gradient, the del operator dotted with our vector field f, 4x cubed plus sine of y squared plus 4y, comma, 4y cubed plus cosine of x squared. So del is the vector of partials, so the first vector of partials, so that would be the vector of the first component, the partial of first component with respect to x, so that gives us 12x squared, plus the vector of the second component, the partial of the second component with respect to y, so we get 12y squared, which is 12x squared plus y squared. So now our Green's theorem says that this vector field is equal to the double integral of the region of 12x squared plus y squared dA. And now when we think about what this region looks like, we're describing the area or the region with radius 2. This is our curve C. And so if this is our region R on the inside, enclosed by this region, now we can use polar coordinates. Because now we're in a place where we can describe this. So using polar coordinates, we have our R is an element of 0 to 2. We're describing the entire circle, so theta is an element from 0 to 2 pi. So this means our region is equal to 0 to 2 pi, 0 to 2 of 12r squared, doing our polar substitution, r d theta for a Jacobian, which gives us 2 pi times 3r to the 4th, evaluated from 0 to 2, which gives us 96 pi as the flux across that closed curve. So using the idea of the region, so if the area of the region, if we have an area of 1, from earlier on in calculus 3, we defined the area of a region to be the double integral over the region evaluated with the integrand of 1. So using the idea of a closed curve, if we bound the region with a closed curve and we choose our vector field such that the curl of the vector field equals the vector 0, 0, 1, we dot that with a k vector, so we get an inside piece that equals 1, then we've found the area of the region. So some helpful choices for our vector fields are negative y comma 0, 0 comma x, and negative 1/2 y and 1/2 comma 1/2 x. The choice of f depends on what problem you're working with, and we'll see some different ideas here. So let's find the area of the curve r of t, the area enclosed by the curve r of t equals t minus t cubed, comma t squared. So let's first off make sure that this curve is closed, that we start and stop at the same point. So at t equals -1, r of -1 is equal to the vector 0, 1, and r of 1 is equal to the vector 0, 1. And so we start and we stop at the same place. So this makes perfect sense. So our area of the curve here is equal to the double integral over r dA, which is equal to the integral of C of some well-chosen vector field So if we say the integral from -1 to 1, and let's choose our vector field f as -y comma 0 dotted with our curve r prime. So let's see, r prime is equal to 1 minus 3t squared, comma 2t. And here I'm choosing f equals -y comma 0. I'm making that particular choice. I could have chosen any of the other three helpful choices, but I'm choosing this one in particular. And you're welcome to try different ones as well. And so substituting this in, so I get -1 to 1, substituting in my y component, so I get -t squared comma 0 dotted with 1 minus 3t squared 2t dt. So I get this as the integral from -1 to 1 of -t squared parentheses 1 minus 3t squared dt. And this is easy to solve. So this double integral is, rather the single integral is easy. So we see that this is the integral from -1 to 1 of -t squared plus 3t to the 4th, multiplying in the t squared dt. So this evaluates to be -1/3 t cubed plus 3/5 t to the 4th, evaluated from -1 to 1. So we get -1/3 plus 3/5 minus positive 1/3. So we get -1/3 plus 3/5 minus a positive 1/3 plus 3/5. Plus 3/5, 3/5, which gives us -2/3 as our final answer. We should have that be positive because we have our area here. So let's see here. So we have -1/3. We cube it, so we get -1/3, so 3/5. So negative, so we insert 1/3, so we get positive 1/3. 3/5, that becomes 3/5. So we get -1/3 minus 1/3. That's -2/3. 3/5 minus 3/5. So we should get -3/5. And so we should take the absolute value of that to get our area. So we get 2/3 as our area. So let's look at an example here where we're finding the disk of radius 5. So from geometry, we know the area of the disk of a radius 5, area equals pi r squared. So radius 5, we should get 25 pi. So we know this from geometry. So using calculus, the area of the disk of radius 5, dA, is equal to the area bounded by the curve f, dr, for a well-chosen field f. And we want curl of f to be equal to 1. And so here, remember our choices for f. We had f is equal to -y comma 0. We had f is equal to 0 comma x. And we had f is equal to -1/2 y comma 1/2 x. Those were all well chosen fields f. So let's look at the double integral over the curve. So we know our area. So if we're looking at the curl 0, f dot dr, and we're looking at the definition of our integral of the cross product dot k dA. We know that if our curl is equal to 1, this gives us our area. And we know that our curve C is parameterized by R of t. The outside of the curve is equal to 5 cosine of t, comma 5 sine of t, and R prime is equal to negative 5 sine of t, 5 cosine of t. So we know these two statements are true for t is an element of 0 to 2 pi. So we know that that bounds our region. And so when we're finding our area for a well-chosen field f, if we find our well-chosen field f for our initial curl here, if our time goes from 0 to 2 pi, given a well-chosen field f, dotted with r prime, negative 5 sine of t, comma 5 cosine of t, dt, this is my f, this is my dr. If I choose my f appropriately, then I can get some things to cancel out. So this is where I'm using some understanding that of properties of my integral. If I choose y, negative 1/2 y and 1/2 x, my negatives will cancel out my dot product. My y is my cosine, or excuse me, my sine. So I'm going to get a sine squared and a cosine squared. So I will get the integral from 0 to 2 pi of negative 5/2 sine squared, or excuse me, sine of t, comma 5/2 cosine of t, dotted with negative 5 sine of t, comma 5 cosine of t, dt. So I get 0 to 2 pi. Doing the dot product, I get negative 5/2 sine t times negative 5 sine t. So I get negative 25, positive 25 halves sine squared of t plus 25 halves cosine squared of t dt. And now my Pythagorean identity says the sine squared plus the cosine squared drops out, and we factor out the 25 over 2 dt, which gives me 25 over 2 from 0 to 2 pi, which gives me 25 pi. So my choice of the other vector fields f would have still gotten me to 25 pi, except for I couldn't have used the Pythagorean identity. I would have had to use either a u substitution or another trig identity to get there. So understanding what sort of properties I might need to use with my vector fields is helpful to know which of these particular options might be useful. And again, these are only 3 of many possible options, but they're 3 very, very helpful options. So the next video we'll do some examples. So as always, if you have any questions, let me know.